So hi everyone, welcome to the online seminar on the mathematical foundations of data science. Thanks for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real pleasure to introduce the distinguished speaker today, Professor Eric Tchetgen from University of Pennsylvania. Professor Tchetgen is the Ladi Family President's Distinguished Professor of Statistics at Wharton School of Business. He has made fundamental contributions to semi-parametric statistics and causal inference. He has won many prestigious awards, such as Myrtle Lefko Polo Distinguished Lectureship this year, Society of Epidemiologic Research and American Journal of Epidemiology Article of the Year in 2014, and Kenneth Rothman Epidemiology Prize in 2011. His primary area of interest is in semi-parametric efficiency theory with applications to causal inference, missing data problems, statistical genetics, and mixed model theory. The title of his talk today is Selective Machine Learning of Doubly Robust Functionals. Please join me in welcoming him.
Thank you so much for the invitation to speak. Zhaoran, Tuo, John Wei, and Zuo Ren and Yao for organizing this seminar. It's a real pleasure to be here and a real honor. I want to share some work that I've been doing with Yifan Kui, who is a postdoctoral fellow at Wharton. Much of this work is actually his product. Hopefully Yifan will be available to answer questions throughout the talk via the chat or towards the end of the talk. So I want to give him credit where credit is due. So the general background of this talk is basically about recent progress in modern semi-parametric theory that have tried to incorporate the use of machine learning when the goal is to estimate functional of interest. In any such examples, the one I'm going to focus on today is one that we care a lot about in causal inference, that is estimating the average causal effect of an intervention. And so the left-hand side of this equation, the mean of YA, is the outcome we would observe if, possibly contrary to fact, everyone was treated with an intervention level little a. So imagine little a is equal to 1 as a binary treatment variable. This would be the potential outcome mean if I were to intervene and treat the whole population with this intervention. And we typically would be interested in the contrast of these kind of factual means. And it's well known that on confoundedness assumptions, this is identified by the right-hand side as a function of the observed data under certain conditions I will review in a few slides. The goal here is to estimate this functionals, the left-hand side called side theta. And it's a finite dimensional functional. In this case, it's just a number, a real number, R1, on a semi-parametric or non-parametric model. And so M is a collection of all laws here that yield a regular model. And we're interested in estimating this functional psi. Estimating psi in most such settings involves a first stage estimation of a high dimensional nuisance parameter. Here in this case, you might think of, I first need to estimate this conditional mean of y given x and a. And I imagine that x is high dimensional, it's sufficiently high dimensional that I cannot do so fully non-parametrically. And so I might need to impose some assumptions or use flexible methods that try to exploit some structure in the data. So highly adaptive method. An important goal in semi-parametric estimation is, even though I need to estimate the mean of y given x and a, I need not necessarily find an estimator that minimizes the mean squared error of that mean. My goal is really to find an estimator that has very small bias for the average causal effect, because that's what I really do care about. Obtaining this regression, obtaining this object, learning about this high dimensional nuisance parameter is just a means to an end. I really do ultimately care about the average causal effect and reporting an estimate of psi that has as small bias as possible due to having estimated theta hat indicating the conditional mean of y given x and a, and the density, the joint density of X. Typically, one would use the empirical for the joint density of X here, but not always. In some cases where that's not necessarily the right thing to do. Now, the state of the art for achieving this goal currently is known as double device machine learning, which has two essential ingredients, and I'm going to review very briefly here. The first ingredient is to, you have to do a little bit of work to identify a moment equation, so an estimate equation for psi, which will typically depend on the nuisance parameter theta. But you want to find such an estimate equation that has a locally robust property that's given here, that if you were to take the derivative of the estimate equation in the direction of the nuisance parameter, any direction in the nuisance parameter, the estimate equation will remain unbiased. Now, this is great because typically such estimate equations have the property that they would have mean zero if you were to put in the correct value for psi and the correct value for theta. And so we want a special kind of estimate equation. We want a special equation that has this kind of robustness to certain perturbations of the nuisance parameter. Okay? This property is typically satisfied by influence functions. So I will discuss influence functions in a minute. But going back to DDML, so once you have such an estimate equation, such a moment equation, and there are many ways of obtaining one such equation, you use cross-fitting to construct psi hat, which solves the empirical mean of your moment equation equals zero, where you plug in a preliminary estimate of theta, called theta hat, which is obtained from an independent random sample from the one that you use to estimate psi hat. Okay? And so this is an empirical version of the moment restriction that U identifies theta. So you have a requirement that the moment U is actually identified theta in the population. And this is just a sample version of that moment restriction. And you obtain an estimate of psi hat. Okay. The move here with cross-fitting allows you to be actually quite liberal in terms of what you can use to estimate theta. And surprisingly, you essentially only require that in order to obtain Wharton inference about psi hat. So inferences we're typically used to, that psi hat basically essentially locally behaves like a normal distribution centered at psi with variance that can be characterized from U. And the condition that you require of theta in this case is essentially that it has rate faster than n2 minus a quarter, which is considerably slower than rates required by parametric models, but it's still somewhat of a stringent requirement. Okay. All right, so our goal today is essentially going to address one issue with double device machine learning, which double device machine learning presumes that you have identified a learner that you're going to use here a priori. Okay? And so the question we are asking is, given the growing number of machine learners out there, how best to select the first stage estimator for the nuisance parameters theta hat? And so I want to suppose I have a collection of k learners, theta hat 1 to theta hat k. Some of them could be random forest, lasso, gradient boosting trees, deep neural nets, you name your favorite. And I obtain these estimators from one half of the sample. And I want to decide which of these estimators should I use for the nuisance parameter in order to estimate the functional of interest, the average causal effect, psi, with small bias. Okay, how can I ensure that I have small bias? And this is important because, as we know very well, there is necessarily no universal machine learner out there. Depending on your data set, one machine learner might do better than another. So you want to be able to adapt, and many of these adapt very well to your data set. But I want to adapt not so much in terms of minimizing the mean squared error for my nuisance parameter, but rather to target the function of interest, the causal effect, with small bias. Okay? And so we're essentially interested in a machine learning selection problem, where I'm ultimately going to use a particular selected model, and so K hat tells me which one I'm going to use, and we want an algorithm to make that decision such that we get close to achieving our goal of ensuring small bias for the function of interest. Okay? So upon selecting that nuisance parameter, data hat K hat, the next question is how to perform post-selection inference in light of this selection step, the uncertainty in which learner is the best learner. So I'm going to present some progress we've made to address both of these questions for a very large class of functionals which admits a doubly robustness property. Okay? This double robustness property, which is not a requirement for DDML, turns out to be something that one can leverage when it in fact holds, to learn something about what it might be the best learner for the data set you at hand. So before doing so, just a brief review of some basic semi-parametric theory and influence functions. Our basic object is going to be influence functions, and these influence functions we'll use them as moment equation. And so in the Chernow-Zhukov framework of DDML, the point is, if you know what the influence function of your functional is, you can always use that, and you're always guaranteed by definition to have the small bias property. And so that provides a general answer to the question of what moment equation should I use to guarantee small bias in a DDML framework. The answer is use an influence function. It will always ensure that property. And I think they do talk about this in their paper. And this is, in fact, something that has been known for quite a while, going back to work by Bickel and Yui and others, and Jamie Robbins and others. So an influence function is a fundamental object of semi-parametric theory that allows us to characterize a wide range of estimators and their efficiency. So it's a theory that allows you to really study semi-parametric efficiency without having to think and trying to be clever about any estimator. You can characterize the influence function of all regular and asymptotically linear estimators, and this allows you to study efficiency theory and robustness properties from a fairly theoretical framework that does not require you to think carefully about a given problem, just applying the tools from semi-parametric theory. So the influence function of a RAL estimator, which this is the way it's typically presented. So a RAL estimator is a regular asymptotically linear estimator, psi hat of psi theta, where theta belongs to a model M, is a random variable, and I'm going to use 12O to denote all the data at hand, observed data, based on ID samples OI. So this influence function will use IF to denote it. It depends on theta, which is a nuisance parameter. It will typically also depend on psi, but I've suppressed the notation, the dependence on psi. Okay, and it captures the first order asymptotic behavior of psi hat, such that scale differences between psi hat and psi theta, the true parameter value, behaves roughly like a scale sample average of ID terms. So you get automatically just a low OP1 term, and this also leads to justification for using the central limit theorem, and IF will then characterize the variance of psi. And it turns out that IF also has some nice robustness property. IF will typically, will generally have mean zero at the true parameter value, and so can be used as an SD equation or a moment equation. It serves as the basis for DDML and will also be used in our work today. The set of all influence functions, so you can always start from a particular estimator and compute the IF, but if you don't want to do that, you don't have any estimator in mind, you can find all IFs and use them to generate the estimate equation. And the theory of semi-parametric theory tells you that the set of all influence function of all regular and asymptotic linear estimators of a given function of interest, like the average causal effect, on a semi-parametric or non-parametric model M, is contained in the Hilbert subspace of mean zero random variables U that solve the following integral equation. So you take a derivative of your function of interest in the direction of a particular perturbation of the underlying data distribution. And that turns out that derivative has a dual representation as the inner product between a random variable U and the score in the direction in which it perturbed the underlying data generating mechanism. Any function U that satisfies this integral equation is in fact an influence function. And so the question is, given a particular functional, you can go through the calculus of generating all such integral equation and characterizing all solutions to those integral equations. And there are many tools. There are textbooks on how to do this. Going back to Bickel, Van der Vaart, Newey has also written a number of papers of that. Cialis has recently written a book. Robbins and van der Laan also have a textbook treatment of this kind of theory in the context of missing data and causal inference. So this is fairly well-developed theory that has a lot of literature widely available. Okay. So we're going to focus on a particular class of problems. So these are going to be problems where we are interested in a finite dimensional functional on a non-parametric or semi-parametric model. So a semi-parametric model that might have some restrictions. But we have been able to show that the influence function has a certain double robustness property. So we'll focus on a large class of doubly robust influence functions. The underlying law O of the observed data O is indexed by two parameters, the parameter theta1, which is going to index the law of covariates f of x. And so in the causal inference context, you might think of x as just simply being the measured confounders. And then we're going to have a variation independent component of the parameter for the law theta2, which contains components of two functions, b and p. And x is r-dimensional. B and p are going to be functions of x. So these are going to be nuisance parameters that index my influence function. Suppose such that the functional side theta of interest has a first order influence function of the following affine form. Okay, that the influence function for the parameter of interest is some random variable that depends on both b and p. Okay, note very importantly that the influence function does not directly depend on the law of the covariates. Okay, and this function h of b and p takes the following linear form. You get a product term in b and p and two linear terms in b and p, and corresponding functions of the data that multiplies these functions. And then you get an intercept function of the data. Okay, and so for different functions, from different functional side, the influence function will take up this form for a particular object b and p that index the observed data distribution, and for particular forms of functions h1, h2, h3, and h4. Okay. What's important about this structure, this is very general and very generic up to now, and I will drill into the specifics in a couple of slides. What's important about the influence functions that have this form is that they satisfy double robustness property, that in order to estimate psi as a solution to the game you're going to play, is you're going to use this as an estimate equation and set it to use its empirical mean. And we worry that we need to specify b and p correctly. And so this class of influence function, as shown in a paper with Jamie a few years back, satisfies a doubly robust property that if you misspecify one of the nuisance parameters, either b, you put in a b star garbage, but you put in the right p, or you put in a garbage for p, you put in p star, but you put in the right b, is exactly matches the mean if both were at the true value, and identifies your parameter of interest psi. Okay, and this will hold for all b star and p star in the parameter space. So there are many functionals that have an influence function in this class. I'm leaving a few here, which is by no means exhaustive. Expected product of conditional expectations, assuming full data functional when data are missing at random, semi-parametric regression, so on and so forth. IV problems, so-called double negative control of unmeasured confounding problems, and estimating the average treatment effect under no unmeasured confounding, which is going to be our running example today. Okay, so I'm going to introduce the running example. So suppose we've observed random ID samples O, where A is a binary treatment, Y is a univariate response variable, and X are features, collection of features or covariates, and which in this case are common causes of A and Y, confounders of the effect of A and Y. And we wish to make inferences about the average treatment effect, which is the average of the counterfactual difference between two possible interventions. One where I force everyone in the population to receive the treatment, and another one where I force everyone in the population to receive the control treatment. Okay. And so that's what we wish to identify. Three important assumptions are sufficient for identification of the average treatment effect. So this is a little bit of causal inference: consistency, durability, and positivity. I'm not going to get into that. The bottom line is, as I said in the second slide, under those assumptions, the average causal effect is identified by the so-called G formula or interventional formula, depending on the background. We will focus throughout on just one arm of this problem, the arm where for the counterfactual mean of Y1, if I repeated everyone, these three identified functionals, the parameter psi naught is identified by the expectation of the conditional mean of the outcome given p equals 1 and x. And the first order influence function, which is now very well known in the literature, takes the following form given in this equation. And what's notable is that it depends on two objects. It's going to depend on the propensity score relative to equals 1 given x, and it also depends on the outcome regression, the mean of y given equals 1 and x. Okay. And the important property of this estimate equation, two important properties. First of all, if all of these are evaluated at their true value, it will have mean zero only if psi naught is in fact a true causal effect under the stated assumptions. And it's also doubly robust. It belongs to this doubly robust class that we introduced, where I'm going to denote P in a slight abuse of notation. P is actually 1 over the propensity score, but I'm just going to call P the propensity score and just to simplify the notation. And then B will be the outcome regression. Okay, so this estimate equation, this influence function, can be rewritten as a member of that class that we introduced, and we'll use that to motivate the rest of the talk. So that's background. Now let's go back to our goal. Our goal is we have a collection of learners now for the propensity score. The learners for the propensity score indexed by K, and we have a collection of learners for the outcome regression. Okay, so for each pair of learners, we can evaluate the conditional mean of the influence function under that learner. For now, let's play this mind game where we imagine we're at the limit or rather that we've estimated the learners from half of sample and we're conditioning on them and just not include the hat in there. Okay, so what's going to be essential for our approach is we want to find what is the best learner to use here for P, for the propensity score, and what is the best learner to use for B, and not so much to minimize the mean squared error for the propensity score or to minimize the mean squared error for the outcome regression, but rather, in a sense, to reduce the bias in estimating psi. Okay. And so for each possible learners, we get a parameter psi KL, and we can use the following, we'll make use of the following object, which is a perturbation for a given fixed index pair K0L0. So I'm looking for a pair of propensity score and outcome regression that are going to do well in terms of bias. And I'm going to introduce now an algorithm to do so. This is going to involve this perturbation function, which is if I'm sitting at a particular candidate pair, K0L0, looks at a perturbation in the functional if I move from the pair K0L0 to another pair of learners, KL. And we're going to use this notation pair. This last two indices always tells you what you're sitting at, and then KL is how you perturb them, okay, the functional. Now we'll consider unidirectional perturbations, okay? We'll consider a perturbation from K0L0 in the direction of the outcome model. So I move from psi K0L0, so the K0 machine learner for the propensity score, the L0 machine learner for the outcome regression. And then I contrast that to psi K0L for a new learner L, okay? And that perturbation turns out has this very simple form. And what's notable about this form is that if in fact, so you get the bias of the propensity score K0, which is the true propensity score divided by the your learner for the propensity score minus 1. And you get the inner product of that multiplied by the perturbation in the outcome direction. And so what's important about this is that if I in fact have identified the true propensity score, it doesn't matter how I perturb the outcome regression. It doesn't matter what the value of L is. This bias term will always be exactly 0 because P over P coincides with 1, obviously. And this is a symmetry to this problem in the sense that now I could perturb K0, L0 in the propensity score direction, and I likewise get the difference in the L0 learner and the true function of the outcome regression, and the perturbation from K0 to K. And likewise here, due to the double robustness property, if in fact my learner BL0 is the true, then I would incur no bias at all. The perturbation will be exactly 0, regardless of the nature of the perturbation, regardless of the choice of the learner K. Okay, and so what we're going to show is that in fact we can leverage this property of double robustness property to find learners that optimally minimize these perturbations. And in a sense, we're going to look for a pair of learners such that if I perturb in either of these directions, the functional psi at that pair of learners, K0, L0, remains fairly stable. So this is robust to these univariate or unidirectional perturbations. And we know that that's a property that will certainly be satisfied if I picked the correct model for both K0 and L0. And we're going to try to leverage that to then select what is the best pair of learners in terms of these satisfying robustness to these types of perturbations. So that's kind of the key idea. If you understand that, you understand the rest of the talk, which is basically just providing details on how to do so. So we define the pseudo risk, which from K0, L0 considers all perturbations where I'm perturbing one object at a time. Okay, so I can either perturb L, and I get all the perturbation. I take the max over all those perturbations, and then I perturb K, and I get the perturbation. And the maximum, the worst case scenario, the worst direction, we call that BK0, L0. That's and we'll name that the pseudo risk. It's not exactly a risk because it in fact depends, typically the risk will depend on the truth and on a candidate estimator. Here it actually depends on the entire collection of learners. And it measures the maximum change of the underlying functional induced by perturbing one of the nuisance parameters at the time and holding the other fixed. So we do this for K0 and L0, and then I can look at all possible pairs K0 and L0, and we're going to evaluate the above perturbations for each pair K0 and L0 given K times L pseudo risk values. And so I'm going to look at these perturbations where each possible candidate pair of learners, let's say I'm using gradient boosting trees for the propensity score and I'm using random forest for the outcome regression. I'm going to look at, given that particular choice of pair, how large is the perturbation when I vary one of those two learners? I substitute a different learner for the ones that I'm sitting at right now, okay? And so we're going to then take the minimal, the pair K0L0 that minimizes this pseudo risk across all possible choices of pairs, and we'll use that as our selected model. And this is a minimax criteria in the sense that it's the pair of learners that minimizes the maximum bias in one unidirectional perturbations. Okay, so we'll use it as a selected model, and then we'll discuss what kinds of properties this model selection procedure has. Okay, K star L star is a pair of learners in the sense that it's the most robust to unidirectional perturbations in this minimax sense. So that's one definition. We'll also define a mixed minimax criteria. Okay, and this one, sitting at a pair K0L0, we call it the pseudo risk, mixed minimax risk. You're going to consider the sum of two perturbations. The first one, first you split K0 and L0. There's going to be one term for K0 and one term for L0. The term for K0, you're sitting at K0, and you look at the perturbation, the maximal perturbation, sitting at K0 and varying the outcome regression. So K0 is a propensity score. You're sitting at a particular learner for the propensity score, and you perturb you look at all possible perturbations of the outcome regression learner. So you look at random forest, gradient boosting trees, lasso, and deep learning, and so on and so forth. You name your favorite. And you take the maximum perturbation holding K0 fixed. So if K0 is correct here, this should be small. Okay. If K0 is not correct, this is going to be very large because K0 is going to be highly sensitive to perturbations in the outcome regression. And then this one is the mirror image where now I hold the outcome regression at my L0 where I'm sitting. And I do the same thing. I look at all perturbations as I vary the learner of the propensity score. Okay. And I sum the two, evaluating the above perturbation for a pair K0, KL0 gives K times L pseudo-risk values. And then we're going to define K bubble, L bubble as the arc min of that risk. And so this is the second kind of minimax criteria, but it's a mixed type because it's mixing these two types of pseudo risk. And we'll see that these two different ways of, and obviously there are a number of ways you can come up with these kind of criteria. All of them have in common that we're trying to leverage the fact that the functional admits an influence function that is doubly robust. And in a sense, the best learner should be one that is least sensitive to changes in one direction. Okay. As we'll see later on, the mixed minimax criteria in fact has a doubly robust rate property, while the minimax criteria does not. The minimax criteria will have a max min rate property. So it may not be entirely the best choice, but we'll see it holds its own, and we analyze both. So this is a special case where you only have two learners for each the propensity score and the outcome regression. And I just wanted to illustrate what these objects look like. So the pseudo risk at model one for learner one for the propensity score, learner one for the outcome regression. The perturbations are going to be I'm sitting at 1, 1, and then I perturb the outcome regression from 1 to 2. And here I'm sitting at the 1, 1, and then I perturb the propensity score. Okay, and I take the maximum of those two perturbations. There are no other perturbations to take. Okay, and likewise for the mixed bias criteria, the mixed minimax criteria. Now we split 1, 1 into two types of perturbation. The first perturbation holding the propensity score fixed, and then I vary the outcome regression from 1 to 2. There are only two choices for that. And then the second one is the one corresponding to the outcome regression. I'll hold it fixed, and I vary the propensity score, and then I sum the two. Okay. We also have an example with 3. I'm going to skip this just in the interest of time, but it just gives you this form. And the point here was to show that, in fact, the mixed bias actually looks at more. Will typically look at a lot more perturbations than the minimax. Mixed minimax will look at a lot more perturbations than the minimax, which might explain part of why it's more. You'll find that it's more robust. Okay. So in order to make this procedure operational, now I have to say, how am I going to do this empirically? I don't actually have access to those risks. I'm not an oracle. And so I'm going to estimate those risks using cross-validation device. We consider a multifold cross-validation scheme, which repeatedly randomly splits the data. And so you can think of this in one split, if that's easier, into two subsamples, a training sample in which we estimate P and V using the learners, and a validation sample from which psi is estimated. Finally, we average the estimated permutations across all splits, and to obtain this estimated perturbation, empirical perturbation, and then we select the empirical minimizer of our criteria. This is the minimax criteria of the estimated risk, and this is the mixed minimax criteria using the empirical estimate of the perturbations under these cross-validation schemes. Okay, so this is just an algorithm that says what are the steps to do to follow. I'm going to skip this as well. It's essentially what I said in the previous slide, just to make sure that I can get through this talk. Okay, so let's talk about some theoretical results. Let's analyze these algorithms. Consider a situation where we have capital K learners for the propensity score, CP, and capital L learners for the outcome regression, CB. And suppose that it turns out each estimator for the propensity score has rate. So if it's a J learner, it has rate for the propensity score mu J. And if it's the Jth learner for the outcome regression, it has convergence rate omega J. Okay. Without loss of generality, I'm going to assume that the best rate, so each of these learners has a corresponding convergence rate. So let's look at the convergence rates of the propensity score. I'm going to assume throughout the remaining of this, for this slide, that the best rate for the propensity score is much faster than the best rate for the outcome regression. Okay, so I can estimate the propensity score at a much better rate than I can estimate the outcome regression. Okay, and so what we're going to find here is we want to understand if I were an oracle that actually had access to the true pseudo risk, okay, value, and didn't have to estimate them from the empirical data, given a collection of learners, and so could actually identify the learner that minimizes our pseudo risk, the minimax learner. Okay, what are the rates of such an oracle? What is the optimality property of such an oracle for each of those two learners? Okay, so we're going to denote mu max as the worst rate for the propensity score and omega max as the worst rate for the outcome regression, attainable rate. Okay, and just for simplicity, let's suppose that you're not adversarial towards yourself, and so you're going to pick at least mu max is not diverging, and omega max are not diverging to infinity. They are the worst constant. Okay. All right. So under Mount conditions, the bias of the minimax oracle selector is of the following form. And so what happens is the minimax criteria is going to give you a square bias, a second order bias. And so this, you can think of this as essentially a constant. It's going to give you, if the estimator is not consistent, if the worst estimator of the propensity score is actually not consistent, and likewise of the outcome regression, but it converges to an object. Okay. So what you get is you get a second order bias, and the second order bias is the square of the maximum minimum rate of convergence between the propensity score and the outcome regression. Okay. And so in a sense, this is the rate of convergence of the oracle estimator in this case, okay, is no better than the square of the best rate for the worst learner between the two of them. Okay, so if it turns out that in fact mu min is root n and omega min is a little faster than n to a quarter, you're going to get here you'll attain close to you'll attain root n. Okay, I think this makes more sense if they are all non-parametric. Okay, and so this just basically states that the convergence rate of the minimax oracle selector is the maximum square of the two rates. Okay, you cannot leverage the fastest rate of the two learners. All right. Well, the bias of the mixed minimax oracle selector will actually leverage the best rate and will recover mixed bias rate, which is the product of the rates of the best rates for estimating the outcome regression and the best rate for estimating the propensity score. Okay, and so this is, in a sense, we can show that if in fact your rate optimal in estimating mu and omega, okay, this estimator will be minimax for the parameter of interest, provided that you have enough smoothness in the propensity score and the outcome regression. Okay. So this, in a sense, the best that can be attained in this context. All right. The second theoretical result we have now concerns the empirical selector. And I think it's best to focus on this first formula that shows the oracle risk. So that's the risk, the pseudo risk attainable by an individual who actually has access to the pseudo risk for the true pseudo risk for each of the learners and can select the best one, and that's the risk that he or she can attain. And this is a selection risk, so that's our empirical version of the oracle risk, cross-validated risk. And this essentially says that you don't incur too much price in terms of being able to come close to the oracle risk. Okay, the difference between the two is roughly of the order of 1 over n. And in fact, K and L here are the number of learners you can look at, and they appear on their log term. And this is very typical to these kinds of excess risk results, where you can actually use an exponential growth number of learners as function of sample size. I don't know. It would probably take you forever to run such a model selection procedures, but it's mathematically possible. Okay, and the key here is the rate 1 over n here. That essentially tells you that and delta, for delta being small, you're almost attaining the oracle risk. Okay. The same result holds for the mixed minimax criteria. This was for the minimax criteria. The proof is actually based on a generalization of some work by Van der Gort and colleagues, which allows you to control exponential tails for second order degenerate using some results by Tchetgen and al. Okay, so remaining time, I'm going to spend the next 15 minutes talking about some empirical results. So the first simulation setup is given here. We generated the net field these functions of x, basis of x that we use to generate the propensity score model in an outcome regression model. And then we're going to compare our methods, this mixed minimax and minimax, to various methods in the literature that use allow for incorporating machine learning algorithms for estimating users parameters. So there's DDML that uses lasso for estimating both objects, double debiased machine learning using random forest, double debiased machine learning using gradient boosting trees. And then we also compare it to targeted maximum likelihood estimation of Land, which uses a superlearner to estimate the nuisance parameters. And superlearner is a stacking algorithm that combines multiple learners for the propensity score and multiple learners for the outcome regression, and finds it's an aggregate of those learners, essentially finds the best convex combination of those learners to obtain a single estimate of the outcome regression and a single estimate of propensity score, and then uses that in the TML algorithm. Okay, so it's a very good method out there. All right. The issue here is, even though it aggregates several learners, it aggregates them to minimize the mean square error of the regression models and not necessarily of the function of interest. Okay, so we're interested in looking at how they perform. So the reference here, so this table depicts for different sample sizes the ratio of the absolute bias of the given estimator relative to the absolute bias of the mixed minimax estimator. And as you can see, if that ratio is greater than 1, then the absolute bias of the mixed minimax will be smaller than the absolute bias of a given estimator. And it's essentially greater than 1 for all of the methods, with the exception of this blip of DDML gradient boosting tree at 1,000 sample sizes. But a larger sample sizes if we establish its dominance. Okay. And so this clearly illustrates, at least in this empirical simulation, that there is some gain to targeting the bias of the functional. Okay, and this can be done even if you are using aggregate or stacking methods to learn these regression functions. This kind of generic algorithms that leverages the double robustness property does have some value in minimizing the bias of the estimators, okay, of the functional, the causal effect of interest. The minimax is at the mixed minimax outperforms the minimax as well, which is not entirely surprising given the optimality results we saw regarding the Oracle versions of these selectors. Okay. So that was the part about selecting a model. The next question is, how do I then perform inferences? I wish not only report a causal effect or a functional, I also want to report confidence intervals. So I don't have much time to go into details of this, but the procedure can be described briefly as follows. We're going to use a smooth max approximation to the selector process, which represents our final estimator, essentially as a weighted average of all possible estimators that you're looking at, where this weight, pKl tau, has a tuning parameter tau. As tau goes to infinity, this weight is going to converge to the indicator that KL is in fact the minimax choice. Okay, selected choice. Okay. For any other value of tau, in practice, we'll use constant value of tau that are not infinity, obviously, and so that will smooth away. It's basically a weighted average procedure, approximation to the selection process. It's fairly standard. A good choice of pKl tau is a smooth function of your estimators. Psi hat KL for each possible pair of choices of your learners, such that pKl tau will go to 1 as tau goes to infinity, if and only if KL matches the optimal choice, empirical choice for KNL for the learners. The smooth approximation, the smoothing over the model selection procedure, allows for approximately valid inferences accounting for uncertainty in selection step, form of learner averaging approach. So we ran some simulations as well to explore the performance of our confidence intervals. These are based on this approach. The last column is the most pertinent one, is the coverage, which method. DML actually performed quite well and control the coverage. For at least for lasso and random forest, lasso did surprisingly well here, even though the selected models, the candidate models, were all misspecified. However, you can see this is the error level for the left side of the confidence interval and for the right side of the confidence interval, and that's the width of the confidence interval. So the trade-off here is for DTML lasso makes up for the bias by providing these asymmetric error rates for your confidence interval. Okay. We focus on minimax and mixed minimax, the proposed method that the confidence intervals have correct coverage, and fairly close to symmetric right and left hand side error rates for the confidence interval, and a fairly reasonable width. It's not the best width of the confidence interval, and that's mainly because we explicitly want to account for the model selection step, and that ends up increasing the confidence interval by a little bit. So what was curious about this simulation is that TMLE actually had a pretty horrendous coverage. And my sense is that TMLE actually might, at least in finite sample, underestimate the model selection step in the first stage where it's using superlearner. And so this is has always been a concern of mine, that unless you have really, really large sample sizes, superlearner being used with TMLE, you might undercover. So of course, this is our simulation setup, but we did not generate data just to be adversarial towards TMLE. These are the results that came out. So in closing, let me just go over an empirical example. We consider this is a classical example in causal inference, looking at the effectiveness of right categorization in the ICU of critically ill patients. So this study considered the effect of RHC on 30-day survival. Data are available on a little under 6,000 individuals, a little over 2,000 of which are treated, and 3,551 are controls. To estimate the additive effect, we use 72 covariates to adjust for potential confounding. And these are the candidate learners that were used for the propensity score and logistic regression with L1 regularization, classification random tree, random forest, gradient Boolean cheese, and these are the candidates for the outcome regression model. So just running quickly through the results. The point estimates actually line up quite well, although the minimax and mixed minimax results match more closely with the TMLE. The confidence intervals for the minimax and mixed minimax results are slightly larger than the others. And this is again a reflection of the fact that we are trying to be as honest as possible about the uncertainty in the model selection step, which always results in wider but correct confidence intervals. It's impossible to know whether they actually have the correct coverage, given that this is one data set. Another observation that I wanted to make was the point estimate is slightly smaller than the point estimate here. I think this is basically, in this application, there wasn't that much confounding going on once you've adjusted for these covariates. And so the model selection step, the machine learning selection step in this case, did not provide grossly different inferences. However, they at the very least provide a sense of satisfaction that in fact the simpler methods that are available here using linear logistic actually gave fairly good results in this particular setting. Okay, so in closing, as we discussed, the choice of the criteria could be more flexible, and we may use different norms rather than L infinity norm. For example, one could use an empirical minimizer of the L2 or L1 norm of the pseudo risk. And the sky is really the limit as to how might you think of leveraging double robustness to select learners for these nuisance parameters. The approach really extends to multiple robust influence functions, and with Balo's son, faculty in Singapore, University of Singapore, National University of Singapore, wrote a really nice paper using this kind of machine learning techniques in the context of invalid IVs, inference with invalid IVs. And I'm going to close here and take some questions. I want to thank UPenn, who put these slides together, and this is really his work. I want to thank him for his hard work on this paper and on the other work we've been doing. The paper can be found on the archive. We're soon going to update it. We just got some reviews, and we're going to update it and repost it very soon. And then references to other relevant work that was cited throughout the talk. And I also want to acknowledge my funding source, which is through the NIH, our grants through the NIH. Thank you so much for your attention, and I can take questions now.
Okay, thank you, Professor, for the very nice talk. So let's go over some questions raised by the audience. And the first question is regarding the two methodologies you introduced. And so what are the pros and cons for different types of pseudo risk you just introduced?
Yes, that is a really good question. So I think basically that relates back to this result, which essentially states that in fact there is, relative to mixed minimax, there really isn't any strong reason to use the minimax oracle selector. The minimax oracle selector is more intuitive in terms of explaining what you're doing. You pick a particular pair of learners, and then you compare, you find the maximal deviation from that learner, the maximum bias, and you minimize that criteria across all possible pairs. And so, in fact, I think this is really the price you pay, is this maximum mean rate that you get the worst of the best rates between the two learners. So if I were to recommend, if you were going to go through the work of using these methods, I would just recommend probably focusing on the mixed minimax. We went through the exercise of studying both of them, even empirically, just to make sure, in fact, that that it outperformed that the mixed minimax outperformed the minimax, and that's what turned out to be the case, at least in our simulation and application.
Oh, okay. Thank you. So another question is regarding the methodology that learns the model. Is it possible to incorporate neural networks in estimating those non-parametric components of the model, and later use your methodology to select a good model?
Yes, absolutely. We did not include neural nets in our own empirical work, but that's and this was mainly because they were very slow, and if you're running 1,000 simulations, but that's certainly of interest, and we're pursuing that. But so the idea is that this is an algorithm that's fairly generic to the collection of learners that you have at hand. In fact, those learners could themselves be aggregates of other learners. You can use and so you could use super learner, get the best outcome regression model you get from super learner, and you just trade as one candidate outcome regression learner. You could use neural nets. There really isn't any. We really wanted it to be fairly generic in terms of the specific learners you're using.
Thank you so much. And the next question is that it seems that in your paper you assume that there are a bunch of models given a priori, and we want to select the best model among them. So my question is it possible to so what if all those models are not very good? Then if we apply those the model selection algorithm, can we just conclude that all of the models are not very good and we need to come up with a better model?
So that is a good question. So that's correct. I'm assuming that you're going to try to do the best possible job available to you. Now, it's possible that this best rate you get from all your candidate learners you're using for the propensity score is actually a constant because you're not consistent, and it's possible the worst rate, in which case the worst rate will also be constant. And so you put garbage in, you get garbage out. What you will get, though, is given your collection of models or of learners, you'll get the pair of learners. For that set of learners, you'll get the pair of learners that is the least sensitive to deviations. And so that is the property that we're aiming for, is what is the pair of learners? Even if they're all bad, it doesn't guarantee that the learner that's least susceptible to these perturbations is any good. It just tells you this is the best you can do. Now, how do you assess that? Well, the way you might assess that is go back and look at the perturbations, because you will have access to the perturbations. So you might actually look at these individual perturbations for your best choice and look at by how much, let me go to the right, let me go to here. You consider perturbation, so you ended up selecting K0L0, and you can actually look at this perturbation and look at how large is how susceptible is my choice of K0L0 to deviations in the outcome regression model or the outcome learner, okay? And likewise in the other direction. So at the end of the day, this is a really good question. At the end of the day, you always want to do this because you might find that you're not willing to live with a particular magnitude of perturbations, and you'll go back and try to get better learners. And so this is by no means the end of all. You can certainly use this as a way of also diagnosing after going through the exercise of using multiple learners, whether or not you're any closer to the truth. Okay. So that's one of the outputs from running these algorithms.
Okay, thank you. So it seems that I'm running out of all the questions, and thank you, Professor Tchetgen again for your very nice talk.